The first web challenge is Club Noob. We're given a URL. If we go to the URL, this radical thing is kind of highlighted. You click on check status, and when you do that, the URL changes and there's this secret phrase thing. If we put radical there instead of nope, we hit enter, we get the flag. The next challenge is robots. Again, we're given a URL that says where the robot's at. If we go to robots.txt, we get the flag. Next is web secret group. We're given a URL. So if we go here, it says the agent is not n00bzadmin. So this is probably referring to the user agent, which is a HTTP header. So to solve this, I have a little solve script. There's a couple of steps, so I'm just going to start from the beginning. First, you do request.get. We pass the URL, and we pass that first header. So it'll look like this. So we're going to request that URL with the headers of user agent n00bzadmin, and then we print out the text. So we do Python 3 solve. Let me make this bigger. And it says does not accept flag. Accept is another HTTP header, and see you can see I already have it here. Accept flag. Let me just copy this out. We run it again, and it says connection is not secure. Basically, you're just going to do this over and over for a bunch of different HTTP headers, every time just adding headers. And I have the solution right here. So we're also going to do connection, and then refer, and give flag. And so once you type in all those headers and you run it, oops, oh, forgot to save, we get the flag. You are now a valid member of the secret group. The next web challenge is conditions. We're given a URL and a download file. So for the URL, you just type in a username. We'll type in some garbage, hit submit. Username is too short. If we look at the source code, there's two checks it makes. There's this login route, and it checks to make sure that the username you provide is less than 40 characters. And if you do an uppercase, it needs to be greater than 50 characters. This doesn't really make any sense. Like, how can a username be both less than 40 and greater than 50? And if we meet those conditions, we get the flag. The trick is that there's Unicode characters that when you convert to upper or lowercase, they actually change the length. So if we just jump into Python real quick, let me copy this character. I found this just by Googling, and there's some Stack Overflow posts that was talking about it. But the length of A right now is 1. And if we do the length of A, and we're doing upper, I think, is 2. Which is pretty crazy. And we can actually see what this is. So this character, when converted to uppercase, gets converted to two S-looking characters. And so that's the trick. We're just going to pass a username that has less than 40 of these. And then when it converts it to uppercase, this is going to be like, 39 times 2. So was that 78? So we can run that real quick. Python 3, solve.py, and we get back the flag. Impossible conditions, more like possible conditions. The first pwn challenge is flag shop. We're just given a netcat port. It says come buy a flag. So if we go to that URL, let's see if it copies. Welcome to the flag shop. The flag costs $1337, but we only have 100. We can buy the fake flag, which costs 50. Since this is a beginner challenge and we're not given source code, you can kind of guess that it's probably going to be an integer underflow. So first, let's check the account balance. We can see we only have $100. So let's try buying some fake flags, and let's buy 3 of them. So our balance at this point should be minus $50. Okay, and so if there is an integer underflow, which it looks like there is, we should be able to buy the real flag. So we'll just ask for 1, and it works. So shop got hacked and flag got stolen. Next is pwn 1. For this challenge, we get a netcat port and a download file. This was a write to win challenge. So if we look at main, it defines a buffer 64 bytes, and then it's going to read in 80 bytes, and then return. And there was a win function defined that calls bin shell. So our job is just to overwrite the stack return address with the win address, and that way we jump to win at the very end. This is what the solve script looked like. We're just going to do some imports, disable warnings, set up some pwn tool stuff, context. It's going to connect to the remote host. And so after flag, that's the output it sends. We're just going to send the win address. I just sent it a whole bunch of times because it's going to fill up the buffer, fill over the RBP on the stack, and then overwrite the return address. And after that, we just jump into an interactive. So Python 3, solve.py. Cool, we have shell, and we do. So we can cat out flag.txt. And there we go, pwn 1 cleared. Now on to pwn 2. The next challenge is pwn 2. It says there's no win function this time. We're given a netcat port and a download file. If we open this up in Ghidra, nice simple main function. This time it's going to do 2 different reads. So we can see we have an fgets here and an fgets here. The first fgets is going to read into this global input buffer for a couple of bytes, 25 bytes, and then it's going to read into this buffer for 96 bytes. So this challenge, there's also no win function. But what's nice is that they call system for us. And the fact that this program is calling system means that there will be a system entry in the global offset table, PLT table, and so we can just call system ourselves as we ROP. So this was a ROPing challenge. And the trick was, first in this input buffer is going to be at a known address. It's not randomized, and so we know what the address of this is. So on our first read, we're going to send bin shell here, and then what we're going to do is we're going to do some ROPing. We're going to find a pop RDI gadget so that we can put the address of input in our ROP code, and then we'll just call system manually with our bin shell as the input buffer there. So not too bad of a challenge. This is what the solution looks like. Same sort of standard stuff, just imports, loading, context, blah, blah, blah. Like I said, the first thing we're going to do is we're going to send that bin shell string. We just need that to exist somewhere. And since we know what the address of input is, that makes it nice and simple. So we're going to, at input, we'll have bin shell. Then we're going to start ROPing. I use Pwn tools for ROPing. It just makes everything so nice and clean. I'll talk about this in a second, but we're going to do ROP.system on that input buffer. So Pwn tools is going to find the pop RDI gadget necessary for calling the system. Like I said, this system call is going to happen on the PLT because it's loaded in the main binary, which is very nice. We don't have to have a libc leak or anything like that. And then after that, we're just going to fill up the buffer overflow. So this is 32 bytes of buffer and then 8 bytes for the RBP on the stack. And then, yeah, we send over the chain and we interact. So we have to do this ROP raw find gadget ret because when you call libc functions in newer versions of libc, they need to be stack aligned. So your RSP has to end in a 0. If it ends in an 8, there's some assembly instructions that get mad. So sometimes you just have to squeeze another ret in there somewhere. So it just moves the stack pointer down by 1 or 8 bytes. And so that way everything's aligned correctly. But yeah, that was the solution. We'll do Python 3, solve.py. We type ls and we have flag. So we can cut out the flag. Cool, exploit without win successful. The next challenge is Pwn strings. We're given a netcat port and a download file. If we go to the download file, nice simple main again, it's going to define some sort of buffer. It's going to ask if we like strings. It's going to read. This is not a buffer overflow. We can see the buffer is 104 bytes and we're reading in 100 bytes, but it is a printf. So we have a printf exploit. That's cool. Then there's this main2 function. If we look at this, what it's going to do is it's going to read flag.txt, read in the contents, and then do a printf on this buffer. If you actually look, it's actually doing a printf on a known buffer. Where is this defined? Let me open this up. It's actually going to read noobs from this global buffer, fake flag here. So this is defined in the data section. But it's strange it's going to be doing a printf on this instead of a puts. And so that's kind of where we're going to exploit it. There's probably actually many ways to exploit this challenge, but I think a very simple way is in main2, the flag is stored somewhere on the stack. And when we call printf, we're allowed to supply, you know, %Ds and %Ss and %Ps and all that stuff, and that'll read variables from the stack. So what we're going to do is we're going to overwrite this fake flag, which is defined in some global variable. We're going to write a %S there so that when printf is called here, it'll actually read the flag variable defined on the stack. And so to set a %S in this global variable, we're going to use that first printf vulnerability to overwrite that data section. To do that, you can have Pwn tools do it for you. We're just going to use a format string exploit to see what that looks like. This is the solve script. So the very first thing we do is first we need to calculate the offset. I'll show how to do that in a second. But then you use Pwn tools, format string payload. So basically using the Pwn tools does everything for you, but under the hood, it's using that %n character, which says is how you write to a variable on the stack, how many bytes you've written so far. You can do a lot with printf. If you're new to the bugs, I highly recommend reading some resources on them because they're pretty powerful primitives if you can find them. But basically what this is going to do is it's going to do this write for us. So at the address of elf symbols fake flag, it's going to write %1 $S. Technically, we don't actually need this. I thought it was going to be higher in the stack, but it ended up being the first one, which was nice and simple. And technically, we don't need this either, but I like to keep it there. And that's pretty much it. So this is going to generate a payload that will write %S to this address. And so then when it calls that second printf, it should just print out the flag. This offset thing, it's not tricky to find. What you need to do is figure out where, when you start typing content, 1, 2, 3, 4, 5, 6, 7, 8, we need to figure out what positional address, what is the positional address of all these A's. And so to figure that out, I usually just do something like this. So I type in a bunch of A's, then %p, %c, %p, blah, 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 and then we count. So we have 8 A's. This is position 1, position 2, position 3, position 4, position 5, position 6. And we can see at position 6, we have all of our A's. And so we know the offset is A. So if instead we were to put like an address here, we could then refer to, this as an address and write to that address, which is kind of what these printf format string payloads are doing under the hood. But anyways, yeah, that was it. So we'll do Python 3, solve. It's going to ring, blah, blah, blah. And here we go. We get the flag. Noobs, format strings are the best. The final pwn challenge is pwn 3. We're given a netcat port and a download file. And it says this time you have nothing. If we open it up in Ghidra, nice short main, it's going to define a buffer. We have a buffer overflow. It's going to be reading OX50 bytes, so 80 bytes into a 32-byte buffer. And then it's going to puts out some garbage and return. If we look at checksec, so checksec file pwn 3, we can see pi. There's no pi, so we have known addresses, no canary, but we're not going to be doing shellcode. So what's interesting is in the previous challenge, system was defined, so we could just call system very easily, but this time we don't know where it is. It's going to be somewhere in libc, but we don't really know. So this challenge is about doing a libc leak, and then we can do a full ROP payload that calls out to system. We've done this challenge, this type of challenge. I feel like this challenge is on every single CTF. So what we're going to be doing is we're going to be leaking global offset table entries. So we're going to be doing 2 different ROP payloads. In our first payload, since we have this buffer overflow, we're going to be ROPing. In the first one, we're going to call puts with the address of puts. To do that, we need a very particular gadget. Specifically, we need a pop RDI gadget. And thankfully, the challenge author was very nice. There's a function here called gadget1. And it's empty here, but if we actually look at the code, we can see we have a pop RDI ret. So what we're going to do, since pi was not enabled, position independent executable, we know where the global offset table entry for puts is, and it's going to be populated with the libc address. So we're going to call puts with the address of puts, which will print out a libc address. And once we have that leak, we can construct a second ROP payload, which will just call out to libc, call out system. Somewhere in system, the string bin shell exists, and from there we win. I also got, I don't know, lucky, but you can kind of assume that the challenge authors are going to be using a newer version of Ubuntu. Technically for this, you should know what version of Ubuntu is. Like I said, or what version of libc. Thankfully, I just assumed they're using Ubuntu 22, and they were. If they weren't, you can leak a bunch of different values of libc, and then use one of the lookup tables online to figure out the exact version of libc, because you do need to know what libc they're using. But like I said, thankfully they're just using a modern version of Ubuntu, which, when I jump into Docker, we're using the same libc. Yeah, that was pretty much it. This is the solve script. Like I said, first we're going to do some ROPing, so set up pwn tools ROPing. Like I said, I'm going to call puts on the entry of the global offset table entry of puts. So we should get the address. And to see what this looks like, let's do GDB pwn 3. Let's do start instruction, next. Oh, whoops. Let's just do run, cancel. So there's the global offset table. So we can see at this address, 0x404018, this address will always be the same. It has this value. So this is the libc address of puts. Once we have this libc leak, we know where the base of libc is, and from there, we can, start doing whatever it is we want. We can see libc this time is loaded right here. And so we're going to be leaking that value at this address. So we're going to call puts with that value. We could leak any of them, but I just think it's fun to call puts on puts. And then we jump back to main. So after we run the shellcode, it's just going to print out that address, and we can calculate where the base of libc is. Now we're going to ROP again. So we're going to do pwn ROP. This time we're passing in libc instead of the main elf. We're going to do this find gadget ret. Again, this is just a stack alignment thing. We had this in a previous challenge. We just make sure the stack is aligned. Then we do ROP system. Normally you don't do this at first. Normally you see if it works, and if it doesn't work, then you add this. You don't just type it. You only need it if you need it. So then we do ROP system. Since we're in libc, libc has the string bin shell somewhere in it. So we just search for it. Since we know what libc it's using the Ubuntu 22, and that's the one I'm using on the system. We just figure out where it is. We call system with that, and then we do another ROP. We know we need to send 32 bytes. We send in some random RBP, and we send over the ROP chain, and from there we should have shell. So we'll do Python 3, solve.py, loading the gadgets, we'll do an ls, and we got shell. Cool. It says if you have nothing, you have libc. So fun. The next challenge is pwn ASM. It says, what can I say except you're welcome? We're given a netcat port and a download file. There's a huge hint in the download file. You can see it says srop me, so we already know what type of attack we're going to be doing. Most likely, we're going to be doing a srop, but we'll see what actually happens. If we load up the binary in Ghidra, we can see it's hand-rolled assembly. So there's a start function and a vuln function. The start function is going to call vuln, and then it's going to call the exit syscall. The vuln function is going to call the write syscall of the buffer message, and it's going to write oxf bytes. Afterwards, it's going to then do the read syscall. First, it's going to allocate 32 bytes on the stack. Then it's going to do 0 into EAX, so it's going to be doing a read syscall, and it's going to read for 512 bytes. So allocates a 32-byte buffer and then does a 512 byte read. So definitely a huge buffer overflow, which is also needed for srop, which we'll talk about in a second. Then it cleans up the stack and it returns. And that's pretty much all there is. So we have a very constrained binary. It looks like we can do some wrapping. This message buffer is interesting. It actually defines bin shell as part of it. So if we took this address 4020000 and we added, I don't know, whatever this is, like 13, 14 bytes or whatever, we have the address, a known address for bin shell. So what we're going to try doing is we're going to try to call syscall. We want to call the syscall for execve, and we want to pass it that address of bin shell. If we look at our syscall table, so the Chrome has these really good syscall table docs. We want to call execve. So this is syscall 59 or syscall ox3b. So that means we need EAX or RAX to be equal to ox3b, and we need to pass bin shell here. We also want these two to be empty. We're not going to pass any arguments, and we want environment just to be null. So this is RDI, RSI, RDX. You can get this from the top of the table. Yeah, RDI, RSI, RDX. Cool. Like I said, the trick that we're going to be doing for this attack is the sigrop or sigreturn oriented programming. So what we're going to do is there's the sigreturn syscall, and it's a beautiful tool for exploitation. It does have valid uses. I think it's used in the signal handlers. But for us, what we can do is when we have a large buffer overflow, we can call the sigreturn syscall, and what it's going to do is it's going to read a whole bunch of stuff off the stack and populate the registers based off of those stack values. And so what we're going to do is we're going to construct one of these sigreturn frames, and it's going to set all of the registers to values we want. So specifically, we're going to set the RDI, RDX, and RSI to the values we need, and RAX. We're going to set RIP such that it points to a syscall. And so when this sigreturn returns, it's just going to jump straight into an execve, which is amazing. There's one little complication. How do we even call the sigreturn? Because there's no pop gadgets, and somehow we need to set EAX equal to OXF so that we can actually call a sigreturn while we're wrapping. Thankfully, it's not too hard. As part of the read syscall right here, when you call the read syscall, it'll set EAX equal to the number of bytes it has read. And so what we can do is we can just we'll call this read call again, we'll just pass 15 bytes to it, and so that way EAX will be 15, and so next time then we can jump to a syscall, and when we do that, EAX will be set, we can jump into the sigreturn, the registers will be populated, from there we jump back into another syscall, and we get shell. To see what this looks like, so standard stuff, just import pwn tools. This is how you construct a sigreturn frame in pwn tools. It's nice and simple. Pwn tools is just absolutely amazing. We need RAX to be equal to that execve syscall. So what would we say it was like 53 or something like that? 59. We then need RDI to be equal to bin shell. Bin shell already exists within the process. We just need to find it. So it was messages plus whatever this length was. If we go back, it's hello world and then bin shell. So we just skip past all of this stuff. We need these to be equal to null. Then RSP, I just set it to some random value, and then RIP is just some random syscall somewhere. So when this returns, it's just going to jump to the syscall, and all the registers are populated. Like I said, we need to get EAX equal to OX15. To do that, we're just going to use the read gadget, and here's just another syscall. So this is what the payload actually looks like. So we're going to do send line afterwards, hello world. We're going to fill up that initial 32 bytes on the stack. We're going to do that read gadget so that we can set EAX to OXF. Then we're going to jump to syscall, so we actually do the sigreturn syscall, and then we put the frame on the stack so that when we call that syscall, everything gets populated. When we do that read gadget, we also need to make sure we send 15 bytes later, and so that way everything's populated. I do 15 minus 1, and then send line also sends a new line. and yeah, you just need to do that. I put a little sleep in here. Anytime you're going over the network, it's good to just add little sleeps in there or do send line after, so it's like waiting on something. Otherwise, I think sometimes the inputs get grouped together, which can be kind of frustrating. And so I think it'll do like all of this as a single read, which is not quite what you want. Yeah, that should be it. So let's run it. Python 3, solve, interactive, ls, and we have flag. So cat out the flag. srop is so fun, right? The first crypto challenge is AES1. It says my cousin sister messaged me on Instagram with this text. We're given a password and a salt and this Java file. So if we look at the Java file, it's just a Java class that's doing some encryption. It's using this password-based key derivative function. It's going to generate some key. It's going to encrypt. And yeah, and they have the password and the salt, and a redacted flag. So the challenge is they used this encryption utility. They encrypted some text. They give us the code, the password and the salt, and the ciphertext. And so basically, we just need to write the code that reverses this. So it's kind of a crypto challenge, kind of also just like a programming challenge. So if you know Java, the challenge really isn't too bad. For the solution, I just copied it over into a valid file. You need the class name to be the same name as the file. So I just named it AES challenge, and I wrote a decrypt function. And so basically, you just kind of take this encrypt function and you do the exact opposite. Thankfully, you can just kind of copy and paste a bunch of code. So we have the cipher. So we're going to get, this is the decrypt function. We needed to get the instance of the AES algorithm. We're going to knit the cipher in decrypt mode instead of encrypt mode. And then we're just going to pass in the ciphertext, and we should get back, this should be the plain text. I'm a little bit lazy, as you can see. But we get back the plain text and we return the plain text. This is the ciphertext we were given. First, it's in base 64. If we look at up here, this is the encrypt method. We can see it's doing base 64 encryption. So we just need to decode the base 64. And yeah, that was pretty much it. From there, we generate a key. This is the same as the previous code. Then we're just going to call decrypt. One thing that might be tricky is you need to convert from a byte string to a string. If you just call toString on it, it doesn't work as you would expect. It's easier to do it like this. You can pass in that byte array into the string function, define a character set, and then print it out. That's pretty much all there was to it. You can either run it in Visual Studio Code like this, and that's running in the background, or you can do Java C. So we're going to Java compile it. It was called AES something. Yep. AES challenge, and then you can just run it AES. And we get the decrypted flag. I don't like AES challenges. Do you like something? Oh, doesn't seem happy with running it. I ran it this time. I don't know why. But there we go. The same thing. So two different ways to run it. The next challenge is crypto maas, modulo as a surface. We're given a netcat port and a download file. If we look at the download file, it's kind of a strange challenge, but basically what's going to happen is we need to guess a 16-character string, and the string is going to be all all the letters in uppercase. And if we can guess this 16-byte string, we get the flag. And so they're going to leak us information about the 16-byte string. We get to give it a number, and it's going to do some modulo with this number and give us the results. And for every one of the 16 bytes, it'll give us 3 of these modulos. So it's kind of like a Chinese remainder theorem sort of challenge or something like that. Yeah, to solve it, it's not the most beautiful solve script. I just wrote it really quick. I just brute force it. So basically, I'm going to pass in for every characters, I'm going to pass in these 3 values. I just picked random values. There's probably a smart way to do things. I was like, they're prime-ish. It also shifts it to the left by 16 bits, which is also interesting. So I was using like 1, 2, and 4, but sometimes I got some duplicates. And when I switched to 3, 5, 7, for some reason it worked better, even though it doesn't really make sense. But this was not a very scientific solution. But anyways, I send in 3 values. I record the responses. And then from there, I just kind of brute force every possible character. I go through every possible character. I see if it matches the conditions. So like, if I pass in a 3, I shift it left by 16 bytes. I do the modulus, and I make sure it equals the out. If all 3 conditions work for that character, I say it's good enough, and I print it out. At the very end, you have to supply back the string that you think it is to the process, and as long as they match, you get the flag. Like I said, there's probably smarter ways you could do this. Like there's probably correct values you could use, but you can just run this a couple of times if it didn't work. But as far as I know, I think it just does work. Just brute forcing all the characters. So we can see it's just sending them all over, just sends a bunch of 3, 5s, and 7s over and over. And this is the final string that was constructed. And here it is, the flag, modulo for the win. The next crypto challenge is RSA. Good old RSA. It says the server's a little bit slow or something. We're given a netcat port and no download file. So if we go to the netcat port, we type it in, Like I said, it takes a second. They put in a sleep in there. We can see we get what looks like some RSA parameters. So we have an E equals 17, a ciphertext, and a N. If we run it again, we can see we get the same E, a different ciphertext, and a different N. So this is a very standard sort of CTF challenge. I think it's called Hastard's broadcast attack. Basically, we're going to be doing a Chinese remainder theorem. Since they're using the same E over and over, and it's the same message, the message is probably the flag. Like I said, we can do this Chinese remainder theorem attack, and we should recover the flag. And yeah, if you want to read more about it, it's called Hastard's broadcast attack, or Chinese remainder theorem. To do this, we need to collect, I think you need about E messages. I collected 20 messages just to be safe. More doesn't hurt. So I connect to the server 20 times. I save all the E, CTs, and Ns. I just make sure that E is always equal to 17. You don't want like a 3 in there or something, which kind of mess things up. And once it's done, I have an array of 20 Ns and 20 ciphertexts. From there, I have some code that just does the CRT. You can also use Sage for this if you want, but some code I found online a while ago and I just have saved that does CRT. Like I said, we're going to do the CRTs, so we just pass in the ciphertexts and the N's, the moduluses, and from there we get the M. Technically, this is the M to the 17th power, because if you think about how RSA is working, so then we need to do the I root of that. So I used GMPY to do this. So we're just going to take the 17th root of that variable and then print out the long to bytes, and we should get flag. So Python 3 solve.py. So it's going to take a second because it has to connect to the server 20 times. Cool, and there we go. Small e is never good.